Greetings everyone. Sarvebhyaः Namaskaraः. Myself MV SUSHUMNA, Assistant Professor in the Department of ECE, PKR College of Engineering. Today I will discuss a topic called adder-subtractor, which is a combinational circuit. So I will discuss today how we will achieve and we will design an adder-subtractor circuit from step by step. Okay. So first, let us discuss about combinational circuits. Digital electronic circuits can be broadly classified into two types as combinational and sequential. Combinational circuits are the circuits where current output, it depends only on the current inputs. There will not be any memory elements. There will not be output always depends only on the present set of the inputs that are applied. So these combinational circuits are faster, easy to design, and since there are no memory elements here, these are always faster when compared with sequential circuits. Sequential circuits, along with the logic gates, they will contain some memory elements to store some bits of information. Since there is a memory, output depends not only on the current inputs, but also on the past history of the outputs. So they will be slower and even circuit will be a bit complicated to design. Today we will discuss about adder subtractor, which is a pure combinational circuit. And let us start discussing about it. First, let us see what is an addition. So we are going to discuss in this order: introduction to combinational circuits, adder, ripple carry adder, subtractor, and adder subtractor. So first, as I already discussed, combinational circuits output, it depends on the current inputs. Since output depends only on the current inputs, these circuits are faster and simple to design, easy to design and analyze also. Now we know that we know how to how to perform this addition in normal day-to-day life. But here we will discuss about the addition of binary numbers, that is zeros and ones. So if you have two binary numbers which consist of only zeros and ones, then we need to add like this. Okay. So here is a 4-bit AND and here is 4-bit added. These two are supposed to be added. Okay. So if you see, these are the least significant bits of this 4-bit number, where the binary weights are increasing from 1, 2, 4, 8, like that, in the powers of 2. So these are the least significant bits. So when we add 2 bits of information, those 2 bits, they can be zeros, 2 zeros, 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 possible combinations. Okay. So in this example, if you see the least significant bits of the first input and the second input, that is AND and added, are 1 and 0. So 1 plus 0, it leads to a 1. Here, if you see the next 2 bits, 1 and 1. When we add 2 ones, the result should be 2. The binary equivalent of 2 is 0 with a carry 1. So in this case, it's a binary equivalent of 2 is 1, 0. That is a 0 and a carry to the next position 1. That is why we get the sum 0 here and a carry bit of 1 to the next position. And again in this case, 1 plus the carry input 1 plus 0 plus 1. So again there are 2 ones here. 1 plus 1, again 0 with carry 1. Here 1, 1, 1. There are 3 ones, and if we add these 3 ones, the result is 3. The decimal equivalent is 3. The binary equivalent of 3 is 1 and 1. That is a sum of 1 with a carry of 1 to the next significant position, most significant position. So this is the result of the addition of these two 4-bit binary numbers. So if we want to design a circuit that performs the addition of two binary numbers like this, then we need to proceed in a systematical way. So we need smaller circuits first to add bits of information, and those circuits can be used in an iterative way to design a larger adder circuit. Okay. Now, design an adder for 1-bit numbers. Okay. So to add these two separate bits, two 1 bits of information, let us take X and Y are two 1 bits. We want to add these 2 bits. So when we add these 2 bits, we will get a sum that is S, and there is a chance of getting a carry that is C. So inputs of our block should be X and Y, which are two 1-bit numbers, and outputs are sum, which is 1 bit, and carry is another bit. So if we form a table for this addition, X and Y, these are the two 1 bits informations. If these two 1 bits are 0 and 0, the sum is 0 and carry is also 0. If these two bits X and Y, one is 0 and another is 1, if you see these two cases, the sum is 1, whereas there is no carry, because there is only 1, 1. The last case where X and Y both are 1s, then the addition will result in 2. That is, the binary equivalent is 1, 0. That is, sum is 0 and there is a carry to the next position. So this is the truth table of the circuit of 1-bit addition. So if we try to implement this circuit using combinational logic gates, we see the carry. Carry is 1 only when X and Y both are 1 and 1. When X is 1 and Y is 1. When both are 1 and 1, then only we are getting a carry of 1. So the logic gate that is used to implement this is an AND gate. And that is why if you see X and Y are given to an AND gate, the output of AND gate is the carry. If we see this sum output is 1 when either X or Y is 1. But both are not 1s, both are not 0s. When one is 0 and the other is 1, then our sum output is becoming 1. So the logic gate that is used to implement this is XOR gate. So we are taking a 2-input XOR gate here and connecting the two inputs X and Y, and output we are taking as sum out. So to implement a simple 1-bit addition, we need for carry an AND gate, for sum an XOR gate. So this circuit is called half adder, which adds two 1 bits of information. This circuit is called as half adder. But in order to perform the arithmetic addition that we discussed earlier, we are getting, when we are adding 2 bits of information, we are getting carry also. And we need to add 2 bits of information along with carry. That is why this half adder is not sufficient for implementing arithmetic addition. We need to design another circuit which can add 3 bits of information. Along with the X and Y, we need to add one more bit that is called carry input. Then only we can achieve that arithmetic addition in a proper way. So half adder is not sufficient for arithmetic addition. So that's why we are designing another circuit called full adder, which can add 3 bits of information. So a full adder is a combinational circuit that adds 3 input bits to generate sum and carry bits. So if we form a truth table For adding 3 bits of information, the possible combinations are, here we are taking X, Y and Z. The possible combinations are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. These are the 8 possible combinations of 3 bits of information. So if we see the first case, all 3 bits are zeros and hence sum is 0 and carry is also 0. So if we see the second and third cases, only one bit is 1, hence sum is 1 and no carry. But the fourth case, 0, 1, 1, here two ones are there. When we add two ones, we will get 2, that is whose binary equivalent is 1, 0. So a sum is 0 and carry is 1. Here again in the fifth case, 1, 0, 0, single one. So sum is 1 and no carry. Again, two ones, 1, 0, 1, 1, 1, 0. Sum is 0, carry 1. And in the last row, we get all 3 bits are ones. So binary equivalent of addition is 1, 1. That is decimal equivalent is 3 ones are 3. Binary equivalent is 1 and 1. So sum is 1 with carry also 1. So if we carefully observe, the carry is 1 in case when XYZ is the min term of X and XYZ is 0, 1, 1, that is 3, and when min term is 5, 6 and 7. Hence we are writing this equation, carry is a function of the 3 variables X, Y and Z, and it is becoming 1 only when this 3 variable function is equivalent to 3, 5, 6 and 7. Similarly, sum is also the 3 variable function of X, Y, Z variables, and it is becoming 1 for the min terms 1, 2, 4 and 7. That is what we are seeing here. So in order to design this circuit, we are taking the corresponding min terms and doing K-map minimization. Corner map minimization gives us the equation for sum and carry. The sum and carry after K-map minimization are like this. Sum is the XOR operation on the 3 bits X, Y and Z, and carry is XY plus YZ plus ZX. So these are the equations for sum and carry after the K-map minimization. Now, a full adder, it can be implemented by using two half adders also. So the same equations we can manipulate and get it in terms of two half adders. Like this. First we will add, in order to add the 3 bits X, Y and Z, what we do is, we already know that a half adder, it can add 2 bits of information. So here we are taking one half adder and we are giving the inputs X and Y 2 bits. This half adder, it will give carry and sum, that is 2 bits of information. To this sum, again we need to add the third bit, that is Z. So we are taking another half adder, and to that half adder we are giving the sum of the first half adder and the third bit that we want to add, that is Z. So this second half adder sum, it will give the final sum up. Now this carry is not the full carry. Again, there is a chance of the second half adder also give a carry. So that is why we are taking 2 carries and then we are adding them to get the resultant carry. That is, we can get a carry here or here. In either case, we are going to get the final carry. So this is how we implement a full adder using 2 half adders. So we clearly know that now a full adder is much simpler circuit where just 3 bits of inputs, 3 input bits are given and their addition output is directly given as sum and carry. Whereas to implement the full addition, we need two half adders. Now, how to build an adder for n-bit addition? Suppose we want to add two n-bit numbers. How to achieve that? By using full adders. We can do it by using full adders. As an example, we are taking a 4-bit adder here. So, to add the two 4-bit numbers, we need, if we go for the normal combinational circuit procedure, it will be a complex circuit to design, because if we take a 4-bit adder, A is one 4-bit number, B is another 4-bit number, then there will be a carry input. So totally 4 bits of A, 4 bits of B, and a carry input. Together we are getting total 9 bits of inputs, 9 input bits, or if we say in terms of variables, 9 input variables. And by adding these two 4-bit numbers along with carry, the resultant output, it can be a 5-bit number, because there is a chance of getting carry in the output after the addition. So totally this combinational, if we want to implement it like a normal combinational circuit, this circuit consists of 9 input bits and 5 output bits, which will be very complex to implement. And it requires 2 power 9 rows of the truth table. So as you can see, inputs are 9, outputs are 5, and the size of the truth table is 512 rows. And we need to optimize output function for each of the 5 bits, 5 outputs. That is 5 function minimizations are required. And that too using 9 variable k-map, which is very difficult. So that is why we go for addition using another method called as ripple carry addition. To achieve the same addition, we will use full adders instead of the normal design practice of combinational circuit. So to add n 4-bit numbers, we just need n full adders. We will take all of them in parallel, and we will propagate the carry just like how we are performing addition by using hand. In that way, we will write the carries of the lower significant bit to the next higher significant position when we are performing addition using by hand. The same way, here also we will connect the carries in that same way to achieve the n-bit addition. Now this is the circuit of binary parallel adder, and here this example circuit, it consists of adding of two 4-bit numbers. So this is a 4-bit adder. So let us say A0, A1, A2, A3. This is one 4-bit number A, where A0 is the least significant bit and A3 is the most significant bit. Now B is another input, another 4-bit input. B0, B1, B2, B3 are the bits of B, 4-bit number B, where B0 is the least significant bit and B3 is the most significant bit. So to achieve this addition, we will use 4 full adders. This is full adder 1, full adder 2, full adder 3, and full adder 4. So for this full adder 1, the first full adder, we will connect both the least significant bits of the numbers A and B and a carry input. And we know that a full adder, it adds 3 bits of information. Here, those 3 bits are B0, A0, and C0, that is carry input. And the outputs are sum and carry. So output sum bit is the least significant bit of sum, that is S0, and carry C1. Now let us connect this carry to the next full adder as the carry input, and we will give the remaining 2 bits of A and B, that is A1 and B1. next bits of A and B and C1. This full adder gives the sum bit S1 and carry C2. Next stage carry C2. So this C2 will be the carry input of the next full adder, and A2 and B2 are the other two inputs. So total 3 bits are A2, B2 and C2. The result is sum 2, S2 and C3. Now again this C3, it goes to the next full adder as carry input. A3, B3 and C3 when added produces sum bit 3S3, that is the most significant bit of sum. And again, there is a chance of getting carry, that is carry output C4. Now this C4, S3, S2, S1, S0 gives the 5-bit result of the addition of A and B. So when added two 4-bit numbers, the resultant, it will be a 5-bit number because of the possibility of the carry. So this is the carry bit, which is in the most significant position. And these are the remaining 4 bits of the sum that we get. Now this circuit is called a ripple carry adder because the carry, it started at this least significant position, and from that position it is going through all the full adder stages to the end of the last full adder. So carry is rippling from one end to another. It is propagating from the least significant section to the most significant section. So that is why it is called as a ripple carry adder. Carry is rippling from one end to the other end, just like in the water, the ripple propagates from the center to the edge of the river. So this is a ripple carry adder. So hence we are achieving here in this circuit a 4-bit addition. If we want an n-bit addition, we just need n full adders to be connected in the similar manner. N full adders starting from the least significant section, propagating towards the most significant section, and the resultant will be an n plus 1 number because two n-bit numbers when added, there is a possibility of carry generation, that is 1 bit. So n plus 1 bit result we will get at the output of the full adders. So this is how we achieve arithmetic addition in digital logic circuits. Not by implementing a complex circuit, complex combinational circuit, but a simple circuit like this, an iterative circuit. This is also called as an iterative adder, where similar full adder sections are used in iterative manner for n-bit addition n times. But there is a drawback for this type of circuit, ripple carry adder, because that drawback is it takes more time. It takes more delay. Suppose in one full adder, if it takes 1 nanosecond to generate sum and carry outputs, in n-bit addition, this second full adder, it should wait for the carry from the first full adder, and after that only we will get the addition result of this second full adder, and after this is produced only the third full adder can complete its action in the same way till the last full adder. So if 1 nanosecond is the propagation delay of one full adder stage, then n nanoseconds is the propagation delay to get the final sum result. So that is the drawback of this circuit. Otherwise, it can perform addition. So it is a bit slow when compared with other circuit, pure combinational circuit. Now, how to perform subtraction using the same circuit? The same adder circuit, same ripple carry adder circuit, it can be used for implementing subtraction also. How it is possible? It is possible by using the 2's complement representation. We know that a number, a negative number, it can be represented by using 2's complement format. So by using that, we can use the same adder circuit to achieve a subtraction also. Subtraction of two n-bit numbers we can achieve. Now let us see this circuit. So this is actually the same ripple carry adder circuit, but in this circuit what we are doing is, see here, the number is A plus minus B. So here we are treating this second number as a negative number minus B. So we know that a negative number can be represented by using 2's complement format. So that is 1's complement plus 1. So this A, it will be given as it is, just like in the previous case. Normally, all the bits of the first input A are given A0, A1, A2, A3 to the corresponding full adders. Now the second number, that is B, it will be represented as minus B, that is 2's complement of minus B. 2's complement is nothing but 1's complement plus 1. So 1's complement means just inversion of all the bits, reverse of all the bits, that is complement of each bit of B. So to achieve that complement, we are taking inverters that are not gates. Inverters are not gates. It will convert, or it will simply invert each bit of B. So B0, B1, B2, B3, all these 4 bits are not connected directly, but connected to the full adder after complementing. That is, they are inverted and applied. So this is 1's complement of B, and we are adding a carry input of 1 here. So 1's complement plus 1, it will give 2's complement of B. So we are representing minus B as the 2's complement and A directly. So we are achieving, and these two are added by using the ripple carry adder. So in other words, we are achieving A plus minus B, that is nothing but A minus B. That is subtraction of A and B. So same circuit, just by giving the second input B through the inverters, that is complement, 1's complement plus 1 is giving 2's complement representation of B, that is minus B. A is added to it. So A minus B is simply achieved by using the same ripple carry adder circuit. So we can use the same circuit for addition as well as subtraction in this way. Now, how to design an adder subtractor, a circuit, same circuit that performs both the functions? By doing a simple modification to the same circuit, we can use it like an adder and subtractor with a mode control input. Now let us see this circuit. This is the adder subtractor circuit. The same ripple carry adder, if you can observe in this circuit, the same ripple carry adder is there. And the first input A0, A1, A2, A3, they are directly given. And the second input B0, B1, B2, B3 are applied to the XOR gate as one input. And the XOR gate outputs are connected to the full adders. Now the third, for all these XOR gates, the carry input is connected as the input, second input. Now this input, this carry input, it will decide whether the operation performed by the circuit is addition or subtraction. Okay, so now let us see. We know that an XOR gate, if one input of the XOR gate is 1, the output of the XOR gate is complement of the second input. It acts like an inverter. When one input is 0, then output of XOR gate is same as the second input. But when one input is tied to logic 1, the output of XOR gate is complement of the second input. So we are using that technique here to achieve both addition and subtraction in the same circuit. Now what happens is when we connect this carry input, now this signal we will use as mode control input. If this input is 0, then carry input of 0 is applied to the full adder, and for all these 4 XOR gates, the one input is tied to logic 0. Then output of the XOR gates is same as the second input, that is B0, B1, B2, B3. So in this way, A0, A1, A2, A3 is applied to full adders as one input, B0, B1, B2, B3 as the second input, and carry input of 0. So it acts just like a normal ripple carry adder, providing the sum output. But in the same circuit, if the carry input bit is logic 1, then what will happen is all these XOR gates, they will invert the corresponding bits of B and apply to the full adder. That is, 1's complement of B is connected to the full adders and a 1 is applied at the carry input. So 1's complement plus 1 means 2's complement of B, that is minus B. A is directly applied and minus B is also applied. So A minus B, that is subtraction, will be obtained at the output of the same circuit. So that is how when this signal is 0, addition will be performed, whereas this signal is 1, subtraction will be performed by the same circuit. So we can call this signal as a mode control input, and if mode is 0, addition is performed. If mode is 1, then subtraction is performed, and hence this circuit, it can be called as an adder subtractor circuit. So this is the ripple carry adder circuit. Now there is one more technique, one more beautiful technique called as carry look ahead addition. This carry look ahead addition is a very beautiful circuit when compared with ripple carry adder, because ripple carry adder, it gives a more propagation delay, as I discussed. If for example, if we assume each full adder, it takes 1 nanoseconds of delay. For n bit addition, we need n nanoseconds of delay. We will get n nanoseconds of delay in getting the correct output. But this carry look ahead technique, it is a faster way of getting the addition output, whereas we will, before only we will estimate whether there is a possibility of carry generation, or if there is a carry, is there a possibility of carry propagation to the next stage of the full adder. At each stage, we will, before only we will assume that is there a possibility of carry generation or carry propagation, and we will design a pure combinational circuit, not an iterative circuit. So the levels of delay is very less. Only 2 levels of logic gate delay will be there. This technique we will discuss in the next lecture. Here we will stop here with the adder subtractor. Thank you for listening. Miss Annie.